So today we are continuing with nuclear chemistry. Please get your pen and your notebook, your chemistry notebook, to jot down whatever you understand in this lesson, because you are definitely going to need them for subsequent revision. Now, let's understand what it is between ordinary and nuclear reaction, because there are different types of reaction. We have ordinary reaction and nuclear reactions, okay? So, ordinary chemical reaction involves electrons, bonds, and energy change in compounds. That's what ordinary chemical reaction, okay? But when it comes to nuclear reaction involves changes in the nucleus, okay? Ordinary chemical reaction, it is only around the electronic level, okay? You transfer electron, you receive electron, redox process, bonding, and so on and so forth. Energy changes. It does not involve the nucleus. But when it comes to nuclear reaction, it involves the nucleus, which leads to the formation of new elements and the release of enormous energy. And such energy is known as what? Radiation. Jamb wants you to understand the difference to be able to differentiate between ordinary reaction and nuclear reactions. Now, let's look at the concept radioactivity. And what is radioactivity? Radioactivity is a type of change whereby the nucleus of an element changes. Okay, there is a change in the nucleus of an element. It's a process, okay? A process whereby a change occurs in the nucleus of an element. Energy is what? Released. So some textbook will define radioactivity for you as, radioactivity can be defined as the emission of radioactive particles by a radioactive element. Such an element that undergoes radioactivity is known as radioactive element, okay? The spontaneous emission of radioactive particle by an element. The spontaneous what? Emission of radioactive particles by an what? Element. Okay? It is natural. When you say spontaneous, it's natural. It's not enhanced. It occurs naturally. That's why I say a spontaneous emission of radioactive particle by a radioactive element or by an element. So such element that undergoes radioactivity is termed radioactive element. So what are the types of radiation? What are the types of radiation? The first we have here is the alpha radiation. This is the symbol, the alpha symbol, alpha radiation. And how do we know alpha radiation? Okay, helium nuclei, alpha particle is a helium nuclei, okay, having the 2p and 2n, okay. Helium what? Nuclei, having the 2p and what? 2n. It is positively charged and has a low penetrating power. Take note of all this. Jamb, when they take all this thing, they play. It is positively charged, it has a low penetrating power, and is stopped by paper. All those small materials when we get power, please stop them. Flexible materials can stop it. It can be stopped by paper, it can be stopped by cellophane. Alpha particle, it will fall. Alpha radiation, it will fall. Stopped by paper, stopped by cellophane. So let's look at the next. The next is beta. This is the sign, the beta sign. And beta radiation or beta particle, it consists of electrons slash what? Positrons. Okay? It consists of electrons slash positrons. Alpha consists of what? Helium nuclei, which is what? Positively charged. But beta consists of electrons, and you know that electrons are what? Negatively charged. So it consists of electrons and what? Positrons. Okay? So we know that electrons are negatively charged. So if they ask you which one is negatively charged, which of the particles is negatively charged, you should know. Or where are negatively charged particles emitted, you should know. You should know that it's beta, okay? Beta radiation. So it has a medium penetrating power, okay? Medium penetration. You know they two they penetrate, but at least they penetrate past alpha. Then make it this center, okay? And it can be stopped by aluminium sheets. It cannot be stopped by paper. If beta particles they come your face, you carry paper put, your face go, it go bombard your full face. Now only alpha if you put paper take block. For beta particles, you can't block it, okay? You can't block it to form a rebound of the particles or the electrons with a paper, but you can use an aluminium sheet to what? To stop it, all right? Then the final we have here is gamma. And the gamma, this is the symbol of the gamma. This is the symbol we have for the gamma, and gamma is an electromagnetic what? Radiation. It is the only different one between alpha and beta because it is electromagnetic, okay? It is electromagnetic. It's an electromagnetic what? Radiation. If you know the revox, okay, revox, you know that gamma is the last. That's acronym used to remember the electromagnetic waves, okay, the revox. So gamma ray is the last in that acronym, and it has the shortest wavelength and the highest frequency. So it has high penetrating power. So it has a high frequency. That should tell you that it has a high penetrating power. And it is reduced by thick lead. So you can only use lead, okay? Lead jackets, lead clothing, lead coverings, lead block, lead. That's only what you can use to stop it. And it's not that it stops gamma ray or gamma radiation completely. To some extent, okay? It reduces it. Okay? That's why when you go to the hospital, you want to do X-ray, you understand? Okay, because of radiation you put on a lead jacket, okay? It doesn't stop it totally or prevent it from hitting you, okay? But it only helps reduce the radiation on you so that your body will not absorb too much radiation that will lead to a problem, okay? Because if your body absorbs minimal radiation, it's definitely not going to lead to a long-term problem, okay? Your body is going to find a way to absorb those radiation and shoot them out, provided that it's not more than it can hold at a time. So let's now look at the methods of detecting radioactivity. How do we detect radioactivity? It is detected with an instrument called the Jamb counter. The what? The Jamb counter. That's what we use to what? To detect the what? The presence of radioactivity. And this Jamb counter was invented by a German scientist. So another instrument used to detect the presence of radiation is photographic plates. Okay, so photographic plates can be used too, and you can also use scintillation counters. We have 3 instruments that you can use to detect radioactivity. The first is what? Jamb counter. The second is photographic plates. The third is what? Scintillation counters. But the most common is the Jamb counter. Now, let's look at natural versus artificial radioactivity. Remember, radioactivity is the spontaneous emission of radiation or radioactive particle by a radioactive element. Spontaneous, there I told you that spontaneous means natural, okay? You are not enhancing it with anything. It just occurs naturally. Broad daylight, it just happen. But you know science now, science don't improve things. So we can't just be waiting for how many years, okay? How many years for half-life to be completed, okay? So that's why the artificial radioactivity came about. So now let's look at the differences or the difference between the natural and the artificial radioactivity. For the natural radioactivity is spontaneous disintegration of unstable nuclei. The natural radiation is the spontaneous what? Disintegration of unstable nuclei. So what's the meaning of spontaneous and disintegration? Let me put it in a simple word, okay? Disintegration means to break, disunity, scatter. Spontaneous means natural. It's occurring on its own. Nobody they enhance them with anything. So you can put this in simple terms by saying the natural, the unenhanced, scattering or disunity of unstable nuclei. Okay, that's what natural radiation or radioactivity. And it is most common in elements like uranium, radium. Very common in elements like what? Uranium and radium. Now let's look at the artificial radioactivity. It is an induced radioactivity. Artificial radioactivity is induced by bombarding stable nuclei with particles. So you induce it, you start it. When you say you induce something, you bring about that thing. Okay, you do it artificially. Manpower, man-made. Okay, man-induced. You induce it, you brought about it. Okay, you brought about it, you established it. Okay, established by man. And how does man establish it? Man establishes artificial radioactivity by bombarding stable nuclei with what? Particles. So if a nuclei is unstable, of course it's going to undergo natural radioactivity. Okay, it's going to undergo natural radioactivity. Spontaneity is going to occur due to spontaneity. Okay, but because of those elements that their nuclei are stable, okay, they are not unstable now. As it can't be say they can't be stable, it still get way be say man go take one. So men started bombarding the stable nuclei with what? Particles. Particles like helium, for example, can be bombarded with some stable nuclei, and is going to what? Disintegrate. Okay, nuclear fission is going to occur. Okay, that's it. That's the difference between natural and artificial radiation. So, and the artificial radiation, for example, it includes production of isotopes in reactors. Okay, nuclear reactors, production of different isotopes. And how does this isotope form? It's formed from nuclear fission. Okay, that's the splitting of a heavy nucleus. We are going to look at all those in no time. Now, let's look at nuclear stability and decay. Stability of nuclear depends on the neutron/proton ratio. The stability of a nucleus depends on what? Neutron and proton ratio. That's what determines the stability of a nucleus. Okay. Now, what is half-life? Half-life is the time taken for half of radioactive nucleus to what? To decay. The time taken for half of that nucleus to decay. If you take 1 year, if you take 1,000 years, if you take 2,000 years, it can take 800,000 years, depending on the nucleus. Okay. So half-life is the time taken for half of the radioactive nuclei to decay. Just always remember when you hear that name, half-life, half. Don't say it's half. The time taken for half to decay. But just know that half-life is time. Okay, it's time. It's a measurement for time. Okay, the time taken. Okay, for half of the nucleus of a radioactive element to what? Decay, or a radioactive nuclei to decay. You can define this half-life in 2 ways. Either way, you can define half-life as the time taken for half of radioactive nuclei to decay. You can also define it as the half of the time taken for a radioactive nuclei to decay. It's still half. The half is still there. So, but it's time That time must be there because it's about time. Half-life is about time. The time must be constant. All right. The formula for half-life is n is equal to n naught, bracket open, half, raised to power t over t, small letter t and capital letter t, where n is the amount of substance remaining after time t. Put this formula for your head. This formula is very easy. The main thing for this formula now, half, which is 1 over 2, raised to power t, small letter t over capital letter t. Very easy. The rest now, n naught. So where n is equal to amount of substance remaining after time. So this small letter t is time. So n represents amount of substance remaining after time. That's after that half time. So the amount of substance remaining. The remaining half nuclear, the remaining half nucleus remaining. So the half nucleus remaining. Now the n naught is equal to the initial amount of substance. The amount of substance we did before the half-life or before the disintegration happen. Then t, small letter t is equal to time elapsed. Okay. Then the capital letter t is what? The half-life of the substance. So depending on what you are solving for, if you are told to solve for half-life, you make this capital letter t the subject of the formula. So if you make capital letter t the subject of the formula, you are now going to be left with t is equal to n naught half, which is 1 over 2, raised to power small letter t times n, just like that. But if you know your basic mathematics, you might not need to do subject of formula. You can just solve everything inside here and still get your answer. But it's risky. Only those that have good foundation in mathematics can easily spot out when they are making mistakes. Okay, but it's always good, advisable to just quickly make what you are looking for, the subject of formula, so that may all those plus and minus things no affect you. This half-life also has an alternative formula. Let's look at the second formula for half-life calculation, because you might be given a question in UTME and they will not give you all of these parameters you have here. So which formula are you going to use? That time in the example, you will not be saying 72 hours to Jamb UTME, no teach us. Mr. Augustine did not teach us, so Uncle Augustine did not teach us this one. I didn't see this one in his lecture note and all of that. No, the half-life also has another formula. Let's look at it. This is the other formula, or the alternative formula of what? Half-life, where you use exponential decay, okay? But this is not so common in Jamb UTME, okay? It is not so common. But the formula is n is equal to n naught e raised to power minus wavelength times time, where this small letter t here is time. This one here, this lambda, is wavelength. E here is for the electron. So this n naught is the actual substance, the quantity of the actual substance, okay? Before the disintegration or before the decay. Then this n here is the substance left, the amount of substance left after the decay. That's the remaining half of the substance. Okay, so you can be asked a question in your Jamb UTME that which of the option is the decay constant. They will put this formula there as part of the option. So what will you do in that case? It's just to pick your answer, just like I have taught you here. That's why you have to jot things down in your notebook. All right, there's one important thing, especially in Jamb UTME. Jamb, they use the set question where they deceive UTME candidates. The question I want to ask you is, how do you know the types of decay? Or the decay types? How do you recognize them? These decay types, how do you recognize them? You know, we have alpha decay, we have beta decay, we have gamma decay. How do you recognize them with their equation? When you look at their equation, how do you recognize them? I will teach you. It's very easy. The first we have here is alpha decay, and in alpha decay, how do you know? The nucleus loses 2 protons and 2 neutrons. The nucleus what? Loses what? 2 protons and 2 neutrons. And in turn, what happens when they lose these 2 protons and 2 neutrons? The mass number decreases by 4. Atomic number decreases by 2. So just have it in your mind that in an alpha decay, mass number falls by 4 or decreases by 4. Atomic number decreases by 2. So mass number, atomic number falls by 2 and 4 respectively. 4 for mass number, 2 for atomic number. That's for alpha decay. And let me show you in the diagram. Now, first of all, we will have to look at what we have on the left-hand side and use that to what? To compare what we have on the right-hand side. On the left-hand side, the mass number here is 238. When you look at the right-hand side, this is the decay form. This hydrogen that you have here is the what? The energy, the radiation given. That's this hydrogen. But this one is the substance formed after this decay. Okay? This is the substance form. And what is its mass number? Its mass number is 234, reduced by 4 or decreased by 4. When we look at the atomic number here, is 92, but here is 90, reduced by 2. This is a what? An alpha decay. Now, let's treat beta decay next. Beta decay. During beta decay, how do you know a beta decay? A neutron changes into a proton plus electron. A neutron changes into a proton plus electron. And what happens in turn? Just bear it in your mind that the mass number remains unchanged. Unlike the alpha decay, where the mass number falls by 4. But here, the mass number remains unchanged. Atomic number increases by 1. Let's look at the diagram. This is the diagram of the beta decay. And in the beta decay, on the left-hand side, we have carbon there, with the mass number 14, atomic number 6. Then, after the decay, we have this as electron, giving off as radiation. This electron giving as radiation. This is the what? The substance or the new nucleus formed after the decay. This is it, nitrogen. Okay? And the mass number is 14, atomic number 7. What changes here when you compare it with the parent nucleus in this equation? Mass number remained unchanged, but atomic number increased by 1. You have 6 here, you have 7 here. 1 electron loss. This is the energy and the radiation released. Now, let's look at gamma decay next. Gamma decay. During gamma decay, what happens? Mass number remains unchanged. Atomic number remains unchanged. Shikina, very easy. Mass number, atomic number remains unchanged. But one thing happens. Only energy is released as gamma photon. So, gamma photon is released in a large quantity because of this high penetrating power of gamma. So large energy is released, better energy they come out for what? Gamma decay. Now, let's look at gamma decay before we quickly come and do a quick recap on this. So this is the equation of gamma decay. Okay, you can see gamma decay. And we have the parent nucleus here, plutonium, having mass number 240, okay, as the mass number, atomic number 94. After the decay, we now had 240 as mass number. We had 94 still as atomic number, remained unchanged, giving out what? Gamma particle as radiation. Shikina, easy peasy. Now, let's quickly go and summarize everything. For alpha decay, what happens? Mass number decreases by 4, atomic number decreases by 2. For beta decay, what happens? Mass number remains unchanged, atomic number increases by 1. Therefore, gamma decay, both mass number and atomic number remains unchanged. Only energy is released in a high quantity as what? Gamma photon. Now, let's look at nuclear reaction. There are two types of nuclear reaction. The first we have is nuclear fission. The second we have is nuclear fusion. Now, let's look at nuclear fission. What's the meaning of nuclear fission? It's easy. The splitting of heavy nucleus. When heavy nucleus splits and release what? Energy as neutron. Okay, so energy is released as neutron. It is used in what? Nuclear power plants. Okay, it is used to generate electricity. Nuclear power plants. And what kind of nucleus undergoes fusion? Uranium-235. Okay, uranium with the mass number 235 undergoes what? It's a common nucleus that undergoes what? Nuclear fission. Okay, so this particular uranium is used as an electricity generator in many countries today, especially the US and Germany. Now, let's look at nuclear fusion. Okay, for the fusion reaction, it means the combination of light nucleus. You combine two light nucleus to form a heavy nucleus. The aim of nuclear fusion is to form a heavy nucleus, a heavier nucleus. That's the aim, the simple aim. So, you combine two light nuclei to form a heavy nucleus. Okay, for nuclear fission, we are forming lighter nucleus. Okay, the heavy nucleus breaks or splits to form a lighter nucleus. But for nuclear fission, our aim is to form a heavier nucleus or a heavy nucleus. And an example of it is hydrogen isotope. Okay, the radioactive isotope of hydrogen, which is the tritium. Okay, the tritium. That is the radioactive isotope of hydrogen, the one that has the mass number 3 and atomic number 1. Now, what in turn happens during this nuclear fission? When these light nuclei are combined to form a heavier nucleus, helium plus energy is what? Given out. So helium particle plus energy is given out, and it is used as a source of solar energy. Nuclear fission is used as a source of what? Solar energy. That's the use of nuclear fusion. Now, let's look at the diagram illustrating nuclear fusion. This is the diagram illustrating nuclear fusion and fission. But let's look at the nuclear fission first, because we treated it first. You can see the illustration. The splitting of large nuclei to give smaller nuclei. Okay? And those smaller nuclei, they are lighter. Okay? That is the aim. You split the big nucleus to give you smaller ones. You can see here we have big nucleus here. It was splitted and it gave us smaller one. Small one 1, small one 2. And particles. This one here is particles. The particles released as energy. Okay? So this is the big nucleus. This one is the big nucleus. This one you have here. Okay? So you bombard it with what? Remember how you do nuclear fission. You bombard it with what? With a particle. If you bombard it with particle, it disintegrates to form what? It formed radioactive barium, form radioactive krypton, and nitrogen as particles. Okay, so if you want to know whether the equation is balanced on both sides, you are going to plus the two mass numbers. So you are going to have 235 here, that plus 1, that's 236. So 236 over 92. So everything here, when you plus everything you have on top here and plus everything below here, you are going to get this 236 over 92. So that's how you are going to know that both sides of this equation is balanced. This 3 you are seeing here is the mole. Okay, is the mole. It is not mass number. That's why it's located at the middle. Okay, it's the mole, not mass number. So that's that for that. Now let's look at nuclear fusion. Okay, what does it mean? The joining of small nuclei together to give a larger one, heavier nucleus, larger nucleus. And how is it done? Okay, we added two small nuclei here. See this one small, see this one small. Okay, helium and lithium to give us what? A bigger one. That's what we have here. Can you see? Radioactive boron. Okay, so if we want to see if this equation is balanced on both sides, we have 10 here on the right hand side, 10 over 5 on the right hand side. Then we should still have the same 10 over 5 on the left hand side. So if you plus what you have on top here, it give you 10, 4 plus 6, 10, then 2 plus 3, 5. Balanced equation. That's that for nuclear fission and fusion. Now, let's look at the steps to balancing nuclear equation. The steps to balancing nuclear equation, I already explained it there, when we were looking at the nuclear diagram, okay, for nuclear fission and nuclear fusion. Okay, but let's just look at what we have here. So the first step is write the parent nucleus, the starting atom. That's the parent nucleus, where the reaction started from, where the disintegration started from. Write it out, okay? Then number 2, identify the emitted particle. Was the particle emitted alpha? Was it beta? Was it gamma? So when you look at these reactions we have here, you didn't see any particle as alpha, beta, or gamma. So how are you going to know the particle that was emitted? How are you going to know? You are going to know with the charge on it. Remember, alpha particle is positively charged. Beta particle is electron negatively charged. So is nitrogen positively charged or negatively charged? It's negatively charged. So this is a beta in form of a beta decay. So we can see this as a beta decay, but remember gamma, okay? Remember gamma. Gamma is the decay whereby the mass number and the atomic number remains unchanged. What changes during beta decay is the atomic number, which increases by 1, okay? Mass number remains unchanged, but atomic number increases by 1. So both atomic number here and mass number here, both remain what? Unchanged. So this is a gamma decay, okay, from nuclear fission. Now, let's apply the conservation rules, okay? You are going to, after identifying the particles, okay, emitted during the nuclear reaction, you are now going to apply the conservation rules, the rule of thumb, the rule that is used, the principle. What are you going to apply? Mass number, top. Now, mass number, the day up. Must balance on both sides, just like we checked just now. The two side balance. Atomic number, the one below or bottom, must balance on both sides, just like we were calculating it just now. Then fill in the daughter nucleus so that both mass and atomic numbers are equal on both sides. Okay, so you fill in the daughter nuclei, all the particles emitted and all the small nucleus emitted. You are going to what? Add electrons to them to balance up the equation. Make sure that what you have on the left hand side balances with what you have on the right hand side of the equation. If you are supposed to minus, you minus. If you are supposed to plus, you plus. Let's look at the diagram illustrating this explanation. Now, balancing nuclear reactions. Okay, balancing nuclear reactions. Look at this one here. Okay, we have uranium 235 and we have nitrogen 1. If you add this to this, you get 236. Okay, so we are left here with 236 over 92. So we have everything has to balance here. 236 over 92. It has to be balanced. So for us to balance it, we were given just this, but we use this one to balance it. This nitrogen and particles emitted. Okay, we used it to what? Balance it. This small nucleus of nitrogen emitted. So from here we have 142 as mass number. We have 91 as mass number. When you add 142 to 91, you are going to get 233. Is it balanced? No, it's not balanced. We have 236 here and we are getting 233 here after adding the two mass number. So let's leave this one first. We know that it's remaining 3 to balance here. Okay, let's now look at the atomic number. 56 plus 36, that will give us what? 92. So the atomic number is balanced. Okay, it balances with this one. Okay, so we just have to add 3. That's why we introduce this what? Neutron and added 3 here as mass number. 3 and 0 as atomic number, balancing everything. So if you add all the mass number here, it gives you all the mass number here. If you add all the atomic number here, it gives you same atomic number here. Simple as that. Shikina. That's what you are going to do. Let's now look at the case where we had to minus. Okay, like this one. Okay, thorium having 234 as mass number and 90 as atomic number. It disintegrates to form particles of pallium and you see these ones, all these ones, and these electrons giving out, the particles giving out. And we have 234 as mass number, but the atomic number here increased by 1 and making this what? A beta decay. That's why you are seeing electron here. So this is a beta decay. So remember how I taught you how to know alpha or beta decay. So to balance the nuclear equation, because you have to keep the equation balanced, whether it's alpha or beta decay, you have to balance the equation. Okay, you have to make what you have on the right hand side tally or commensurate with what you have on the left hand side. So we have 234 here balanced here, then we have 90 here and we are having 91 here. What do we have to do? We minus 1 electron, give it a mass number 0 because the mass number is already balanced. The atomic number minus 1, that tells us that there's minus 1 electron here. So this nuclear equation is balanced. So analyze these last two left and drop it in the comment section if it's balanced or not. Just comment equation 3 and 4 balanced, or equation 3 imbalanced, or equation 4 imbalanced. Just drop it on the comment section and I will reply you if you got it right or wrong. So just look at these last two equations if they are balanced or not. Now let's look at the applications of radioactivity as recommended by Jamb UTME. So the applications of radioactivity includes in medicine, It is used for radiotherapies, whereby we use nuclear particles, radiation from radioactive substance to treat ailments such as cancer. It is also used in diagnosis, okay, to diagnose, to see inside the body, imaging tests, okay. Use it to picture inside the body using X-ray and all other advanced X-rays. You have CT scan, which is the computed tomography, and you have other specialized X-rays like IVU and so on and so forth. So it's also used for diagnostics, like I explained, to diagnose ailments, especially for ailments like cancer, or when the bone fractures, or ailments involving the skeletal system, okay, the muscular system, soft tissues, hard tissues, and so on and so forth. It's also used as tracers, okay. Then in agriculture, radioactivity is used to preserve food. It's also used as pest control, although it's dangerous, but it's used, okay. Industrial use is used for thickness in gauges, okay. It's also used for leak detection, okay, in industries, to detect leak in pipelines, okay, like petrochemical pipeline, okay, water pipelines. You use it to detect leaks, okay. It's also used in power generation, very common, especially in today's world, okay, especially in the first world, the first and second world. Is very common there, the developed countries, okay. So they use nuclear reactors to generate electricity. That's why their electricity are always stable, but there are risks attached to using nuclear reaction or radioactivity to generate electricity. But are there any reaction on Earth that involves no risk? No reaction involving production that involves no risk, okay. There are no solutions to life, only trade-off. What is important is you're balancing those trade-offs and ensuring your safety at all times. Though adverse events occur, but you can always work proactively to help prevent the occurrence of adverse events, or to be ready and responsive to salvaging the effects of adverse events or the aftermath of adverse events, because adverse events must occur. It occurs everywhere. So we can't say because of risk we wouldn't be enjoying the resources we have, we wouldn't be enjoying technologies. No, we try as much as possible to prevent adverse events, but when it happens, we try our best also to salvage the aftermath or the effect of those adverse events. Now let's look at solubility. And what is solubility? Solubility is directly proportional or is equal to mole of solute per decimeter cube of a solvent at a given temperature. Many textbooks will tell you solubility is the amount of solute per decimeter cube. Is measured in cubic decimeter. It's the amount of solute that can dissolve in a solvent at a particular temperature. That is solubility. The amount of solute, you know what a solute is. We have treated this in the introductory part of this chemistry. The amount of solute measured in decimeter cube or cubic decimeter that can dissolve in a solvent at a given temperature. So if you want to plot the solubility curve, now you are going to plot solute, which is in cubic decimeter. You plot it against the temperature. Okay. So I am going to teach you how to interpret the solubility curve. Now let's look at the types of solution. The first, under the types of solution, the first we have here is unsaturated solution. And what are unsaturated solutions? They are solutions that can dissolve more solutes at a given temperature. Solution that can take more solutes at a given temperature. It's just like you bring salt now and water. You continue to add salt to that small water. You add salt to, as you are adding salt, provided that that solution that you have can take more salt. That's the salt is the solute. The water is the solvent. Provided you can continue to take more salt. If you add more salt, it dissolves. That solution is known as unsaturated solution at that given temperature. You don't have to increase the temperature for it to dissolve more salt. At that given temperature, if you put salt, it dissolves. That solution can be called what? Unsaturated solution. It's unsaturated. It's just as if, take this room for example, and people are entering, okay? People are entering at this given temperature, at the ambience, okay? People are entering. Provided that people can continue to enter, we can accept people into this room. We can call this room unsaturated solution. Provided we can continue taking more, okay? Those people that are entering are the solutes. They are entering at this given temperature, no change in temperature, okay? Provided they can continue to enter, it's an unsaturated solution, okay? Now let's look at a saturated solution. Unlike unsaturated, saturated is a solution that contains maximum solute at a given temperature. This solution contains maximum solute at a given temperature, meaning that for that solution to dissolve more solute, you need to increase the temperature. You need to start boiling, maybe. Let me now give you an example with this room. You know that we're accepting people which are the solutes into this room. We are able to accept them, and then we refer to it as unsaturated solution. But the moment whereby this room becomes what? Congested, we can't accept more people into the room at this given temperature. This room is now called saturated solution or saturated room, because at this temperature we can't accept more people which are what? Solutes. Now that takes us to super saturated solution. It is a type of solution that contains more solute than possible to what? Dissolve. Okay, it contains more solute than normally possible. So this solution contains too much solute that it cannot dissolve any solute at all again. Even though you increase the temperature, the solute will not dissolve. That is super saturated. So you can see how it started small, continue to transcend. Okay, it started from unsaturated, People can still enter at a given temperature. Solute can still enter at a given temperature. It enters saturated. People can no longer enter at that given temperature except you increase the temperature. Then it comes from that saturated, enter super saturated. Meaning that people can no longer enter again. Solute can no longer enter the solution again, whether you increase the temperature or you decrease the temperature. That's that for that. Now, let's look at solubility curve. Solubility curve is a graph showing solubility versus temperature. Just like I explained to you. Solute, you plot it, solute in decimeter cube, you plot it against temperature. So, why do we plot solubility curve? We plot solubility curve because we want to know how many solutes can dissolve in a solvent at a given temperature. We use it to know how soluble a solute is. Okay, we use it to know how many solutes dissolve in a solvent at a given temperature. If more solute dissolves in the solvent at a low temperature, that shows that that solute is highly soluble. But if less solute dissolves only at a high temperature, even after increasing the temperature, only small dissolve, that shows that that solute is poorly soluble. Okay, it's a poorly soluble substance. Now, let's look at the facts about the solubility curve and how to understand the component of the solubility curve, how to interpret it. Jamb always set questions from here. You see the solubility curve? You must see the solubility curve for your Jamb UTME. I'm assuring you. So, learn. The first thing is deduction, okay? Under deductions in solubility curve, solubility generally increases with temperature for solid. So, if temperature increases, that's why you increase the temperature. When the solution is saturated, you increase the temperature to dissolve more. So, as temperature increases, solubility increases. For solid, so... But for gases, it decreases. So it's directly proportional for solids and inversely proportional for gases. Okay? So solubility is directly proportional to temperature for solids. As temperature increases, solubility increases. For solids, so, but for gases, it's inversely proportional. Solubility is inversely proportional to temperature. As temperature increases, solubility what? Decreases for gases. Now, the next is the point on the curve, that's the point plotted on the curve, is equal to the saturated solution. The point on the curve equals saturated solution. Yes. The next fact is the point above the curve equals supersaturated solution. So above the curve is the supersaturated solution. They can ask you a question from any of these. The point below the curve is equal to unsaturated solution. So just know that the point on the curve is saturated solution. The point above the curve is what? The supersaturated solution. While the point below the curve is unsaturated solution. Now let's look at the solubility curve. This is the solubility curve. We have two solubility curves here. I'm going to show you the other one. The other one, you are going to interpret it and drop it in the comment section, the interpretation in the comment section. So, we were talking about the point in the solubility curve. Okay. So, for example, let's say this potassium triisonitrate 5, this one now, it has a point here. Let's say this is the point. So, that point is what? Saturated. Then, above the point, that's around here, above the point, is what? Is the what? The supersaturated. Then below the point is what? The unsaturated. So for this graph now, all these places that you have the chemical formula of the salts, here now is the point. 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 So above, below, on the point, you know what should be there. I already taught you. So now, interpreting the solubility curve, I told you, plotting solubility curve, you are going to have solute on the y-axis. That's the vertical line of the graph. Then you have temperature on the what? The s-axis, the horizontal part of the graph, because you are looking at how many solutes can dissolve in a solution. The solution here is water. Look at it, H2O is the solution. Okay? How many of these solutes can dissolve in this solvent? The solution is the solvent. Okay, the solvent. How many of these solutes will dissolve in water at a given temperature? So the temperature here is 30 degrees, 60 degrees, 90 degrees, 120 degrees. The solute, measured in cubic decimeter, 30 cubic decimeter, 60 cubic decimeter, 90 cubic decimeter. So if you trace it here, you see that 1, 2, 3. That's each is 10, 10, 20, 30, 40, 50, 60, 70, 80, 90, and so on and so forth till you reach up. So how are you going to know the least soluble and the most soluble here? Let me teach you. It's very easy. It's very easy. What you have to do is here that it joins on the, where you have the solute. At this place, then you will now plot it to go to where the temperature is. Here. So here. Now you trace it down. At 70, this one is 60. Okay, 60, 70, 89. So at 70 degrees Celsius, 150 cubic decimeter of sodium triisonitrate 5 dissolved in water. That is a high solubility. It is highly soluble. Much of this substance dissolve at a high temperature. Remember that solubility starts in low temperature. Okay, room temperature. That's where solubility starts. Like you bring salt now, put inside water, it will dissolve. You increase the temperature or not. So a substance that dissolves more in a low temperature, in room temperature, That shows that that substance is highly soluble. So that tells us that this substance is highly soluble, but it is not the highest. Okay, it is not the most soluble in the graph. What I'm going to do is I am going to look for the most soluble here and the least soluble here for you. You are going to look for the rest and drop it in the comment section. Okay, now let's look at this one. Since this one is 180, this one is 190, this one is 200, this one is 210. So at the 200 mark, so it means that this one is potassium iodide salt. So it means that 200 cubic decimeter of potassium iodide salt dissolved in water at what temperature? Let's now plot it to get the temperature here. This is the mark where it stopped. Now we trace it down here. Okay, so the first one here is 10, this one is 20, this one is 30. So at 20 degrees Celsius, at 20 degrees Celsius, 200 cubic decimeter of potassium iodide dissolved in water at 20 degrees Celsius at a very low temperature, below room temperature. That tells you that this substance is highly soluble. More of its solute dissolved in the solvent, which is water, at a very low temperature. So we already have the what? The most soluble. Okay, the most soluble, which is this one. Okay, 210. Now let's look at the least soluble. Let's go down. Okay, looking downwards, we have this one. If you trace this one down here, you have 20. Now this one is for you. So what you have to do here, this is another solubility curve. You are going to show me the most soluble salt and the least soluble salt. Drop it in the comment section. The most soluble salt and the least soluble salt. Drop it in the comment section. Now the calculations under solubility. This is the calculation under solubility. Now how do we calculate solubility? It's very easy. For example, you are asked a question: if solubility of potassium thiazonitrate 5 at 40 degrees is equal to 20 mole per cubic decimeter. This is how they normally ask you the question. They will ask you that how many moles does so substance that dissolve in so substance at so temperature. So since it's 20 mole per cubic decimeter, 1 cubic decimeter of the solution contains 20 moles. Okay, per 1 cubic decimeter, it contains 20 moles. So first of all, when solving questions relating to solubility, we are going to do the calculations later. Before you start, the first thing to do is to balance the equation. After balancing the equation, you are going to calculate the mole. Okay, the mole of each substance, each of the elements in this salt or this compound, and you are going to calculate the equal mole, or the mole, which is the molar mass of this compound. Then you calculate the molar mass of each of the element there, and you divide by the smallest. That's one of the easiest way to get moles. Okay. So now you can use molar concept for conversion between mass, mole, and volume. It's very easy. You use molar concept to do your conversions between mass, just like I explained. You are going to find the molar mass of each of the elements here. After looking for the molar mass, you look for the molar mass of the whole compound, then you divide by the smallest to get the mole. Very, very easy. When we start doing the calculations, you are going to see how easy these are. Let's look at solvents and their uses. Solvents and their uses. First of all, we have to understand what a solvent is. Though we already discussed solubility, you should know what a solvent is, since we talked about solubility not quite long ago. But let's define a solvent. A solvent is a chemical substance which dissolves a solute. That place where solute they dissolve inside, now the solvent. For example, water is a solvent and is a universal solvent, and it dissolves solutes. Solutes dissolves inside. Salt dissolves inside. Sugar dissolves inside. So that sugar, that salt that dissolves inside the water is a solute, while the water that dissolves it is called a solvent. Okay, and water as a universal solvent is called a universal solvent because a lot of substances or a lot of solute dissolves in it. Okay, that's why it's called a universal solvent. And it dissolves salt, it dissolves sugar, and so on. I'm telling you the reason why water is called a universal solvent, because it has a wide range of dissolution of solutes. Okay, that's why it's called a universal solvent. Now let's look at organic solvent. We have universal solvent, we have organic solvent. Organic solvent that dissolves organic compounds. Okay, and carbon. Okay, organic solvent also dissolves carbon. For example, organic solvents include benzene, okay, petrol, which dissolves fat, oil, and paint. Okay, all those organic products, petrochemicals. Okay, organic solvent dissolve them. Water can't dissolve them. Okay, then you also have alcohol as organic solvent. When you say organic solvent, it's a solvent made up of organic compound. You have alcohol which dissolves perspiration stains from perspiration, stains from sweating. Sweat. That's the kind of stain that alcohol is capable of removing. So organic solvent is also used in cleaning, especially when the dirt is connected with organic compounds. Okay, the stain was brought about, it was induced by organic compounds. Okay, you can use it for paint removal, you can use it for stain treatment. Okay, but mostly for organic. But for the inorganic ones, they are soluble in water, so you can always use water as a universal solvent to cleanse them. Okay, it's just like give what belongs to Caesar, and give what belongs to God, just like that. So for water, the universal solvent, you use it to dissolve mostly inorganic solutes. Then for the organic solvent, use it to dissolve mainly organic solutes. Let's now take some Jamb must repeat questions to further test the knowledge we've acquired so far. Jamb must repeat questions. Question 102. Which of the following distinguishes a nuclear reaction from an ordinary chemical reaction? A. Nuclear reaction involves 2 electrons only. B. Nuclear reaction involves change in the nucleus. C. Chemical reaction release more energy than nuclear reactions. D. Nuclear reactions do not produce new elements. What's the answer? Drop the answer in the comment section. Question 103. Which radiation has the highest penetrating power? A. Alpha. B. Beta. C. Gamma. D. Neutron. What's the answer? Drop the answer in the comment section. Question 104. Which of the following is an example of artificial radioactivity? A. Uranium decay. B. Radium disintegration. C. Bombardment of nitrogen with alpha particles. D. Spontaneous emission of alpha particles. What's the answer? Drop the answer in the comment section. Question 105. A radioactive element has a half-life of 10 minutes. If the initial mass is 80 grams, what mass remains after 30 minutes? This is a use half-life formula to solve this. A. 40 grams. B. 20 grams. C. 10 grams. D. 5 grams. What's the answer? Drop the answer in the comment section. Question 106. Which of the following is a nuclear fusion reaction? A. Splitting of uranium-235 nucleus. B. Combination of nitrogen nucleus to form helium. C. Decay of radium. D. Emission of alpha particles from uranium. What's the answer? Drop the answer in the comment section. Question 107. A solution that contains more solute than it can normally hold at a given temperature is A. Unsaturated. B. Saturated. C. Supersaturated. D. Dilute. What's the answer? Drop the answer in the comment section. Question 108. From a solubility curve, the solubility of potassium triazonitrate 5 at 40 degrees Celsius is 50 grams per 100 grams of water. How much potassium triazonitrate 5 will dissolve in 200 grams of water at the same temperature? A. 25 grams. B. 50 grams. C. 100 grams. D. 200 grams. What's the answer? Drop the answer in the comment section. Question 109. Which of the following is a colloid? A. Salt solution. B. Harmattan haze. C. Milk. D. Sand in water. What's the answer? Drop the answer in the comment section.